welcome Mark and his team from ETH Zurich.
Welcome to the Flying Machine Arena. The Flying Machine Arena is a space we use to do research on flying machines. The main components are a set of cameras on the ceiling, which look down and observe what's happening in the space, a set of laptop computers behind me that compute actions based on the observations, and then a set of flying vehicles. These quadrocopters that you see around me are the vehicles we primarily work with. In today's public lecture, we want to achieve a couple of things. Firstly, we want to demonstrate the dynamic capabilities of these quadrocopters. Secondly, we want to give you an insight into the work that we do at ETH. And finally, we want to try and convince you that automatic control in general and robotics specifically have amazing potential. Today, the technology is there to have these vehicles revolutionize our daily lives. There are lots of opportunities, though, especially for the youngsters in the audience, to take this technology to do research, to discover new things, or to take the research that's already been done and bring it out into the real world, to commercialize the research. To begin with, let's have a look at how these vehicles actually work. A quadrocopter is a very simple machine. It has only 4 moving parts, these 4 motors. Each motor has a single fixed-pitch propeller. The easiest way to think of how a quadrocopter works is to think of the 4 motors collectively producing a thrust force. This collective force points forward, and it pushes the vehicle forward. With differences between the 2 motors, between the 2 pairs of motors at least, we can rotate the vehicle. For example, if this propeller produces a lot of force, and this propeller does not, the vehicle will rotate in that direction. Likewise, if this propeller produces more force than this propeller produces, the vehicle will rotate away from me. Once we have the vehicle pointing in some direction, we can use this total force to push it forward in that direction. So, how does the vehicle fly? When the quadrocopter is hovering like this, there are 2 forces acting on the vehicle. The one is this total thrust force, which points upwards, and the second force is gravity, which pulls the vehicle down to the ground. For the vehicle to hover, we need these 2 forces to balance one another. We need the thrust force to point upwards, away from gravity, and we need the magnitude of the thrust force to equal the weight of the vehicle. Then the vehicle will neither accelerate upwards nor accelerate downwards. Obviously, for the vehicle to stand still, it needs to not rotate. This means that the opposing motors need to produce equal force. Specifically, if we combine all of this, this means that when the vehicle hovers, we need the 4 motors to produce equal force, equal each to a quarter of the vehicle's weight. Then, if the thrust points upward, the vehicle will stay where it is. We'll let the vehicle hover again. What we'd like to show you now is what happens when we do this, when we just set all 4 motor forces equal to one another, equal at a quarter of the vehicle weight. What we just described, we expect the vehicle to stand still. We will, however, see that this is not the case. I'm going to get a bit to safer distance. I'm going to ask Robin to click a button. When he clicks the button, the vehicle will switch over to constant motor forces, each equal to a quarter of the vehicle weight. Are you ready, Robin? Okay, go. So at the end there, Robin clicked a button to catch the vehicle. We see that the vehicle becomes unstable. It does not stay where we put it. Let's try again. Okay, go. Again, he clicked the button to catch it. We'll do it one last time. Okay, go. So what we see is that the quadrocopter is not stable. It does not stay where we put it in the space, even if we expect that it should. Why is this? Well, the reason is that the world is not as simple as this model we just described. There are things acting on the vehicle that we did not capture with this simple description. For example, if the vehicle is standing in the space and there's a slight breeze which pushes it to the side, the thrust force is now not pointing upwards, but is pointing slightly to the side, and the vehicle will accelerate away in that direction. Also, if one of the propellers was just slightly damaged and produced less force than we expected, the vehicle will roll away. If this propeller produces slightly less than a quarter of the vehicle's weight, and this one produces a quarter of the vehicle's weight, there will be an imbalance and it will rotate left. Once the vehicle is rotated, it will push itself away and it will move in that direction. So we know that to have the vehicle fly and to stay in one spot, we need to do something more. We need to observe what the vehicle is doing and react to these observations. This is the fundamental idea of automatic control. One of the things that we measure to observe what the vehicle is doing is the position of the vehicle. On the two projectors, you will see some of these signals. The top figure shows the position error of the vehicle. That is how far it is from where we want it to be. There are 3 lines, that's one for each direction. So as I move the vehicle around, you see the 3 lines move. I think the green line is for the forward-backward error. One line is for left-right. So as I move the vehicle left-right, you can see the line moving, and then there's a line for the up-down error. What we want to do now is we want to find a way to get the vehicle to move to this position we want it to go to. We want to move this error to 0. To do that, we will use the motor forces, these 4 motors that we have. The motor forces are shown at the bottom plot. At the moment, it's all 0 because the motors aren't turning. We're going to let the vehicle hover and return to its position. Notice that the top plot, the position errors, have gone to 0. The position of the quadrocopter is where we wanted it to be. The bottom plot shows the 4 motor forces. What's important to see is that they're not constant. They're all the time adjusting for tiny errors. We're constantly measuring where the quadrocopter is. We realize it's not at the correct position, and we try to correct for this using the motor forces. I can also pull the vehicle around. When I pull the vehicle downwards, you can hear the propellers. It spins up because it's trying to fight me. The vehicle measures that it's too low, and it tries to push itself back up. You can also see this on the figure. If I pull the vehicle down, an error appears on the blue line, and you can see the motor forces increase to try and push the vehicle back up. If I pull the vehicle to the side, notice how it's rotated. It's trying to push itself back in this direction. We can use the same idea to recover from larger errors as well. We're using the exact same control law now as we used before when the vehicle was hovering. The only difference is that the errors are much larger now. I'll throw the vehicle upside down now. The first thing that the controller has to do is rotate the vehicle the right way up, and then it can bring it back to the hovering position. So I'll throw the vehicle up, and then it has to turn around. I can also try to throw the vehicle out of the space. Make it a little bit harder for the controller. Okay, I'm going to throw the vehicle 2 more times. I'm going to ask that you have a look at the plots. Notice that when I throw the vehicle, the position error will suddenly become very large as the quadrocopter flies away from where it was supposed to go. Then you'll hear the propellers turning on, and you'll see the plot jump as we try to control it back to its original position. Okay. I'll throw it 1 more time. So what we've seen here is that the quadrocopter is not stable. It does not stay where you put it. Next, we will look at another system that is not stable. The problem is to try and balance a stick upright. This is something that I'm sure everyone here has tried, especially the controls professionals. We all know that to keep the stick upright, I need to do something. I need to somehow move the bottom of the stick. So how do I do this? How do I keep the stick upright? Well, the basic layout is as follows. I use my eyes to observe what's happening. Is the stick standing upright, or is it falling over? I then have a rule in my brain that tells me how to react to the stick. This rule tells me how to move my hand, and I can then move my hand, and hopefully the stick will stay upright. Next, we will have a quadrocopter also balancing the stick. The quadrocopter, though, does not have the same things I do. So instead, the quadrocopter will use the cameras to observe what the stick is doing. Is it balancing, or is it falling over? It will then use the computers at the back to choose an action, so to decide what to do to react to whether the stick is falling over. Finally, it will use its motors, the propellers, to move around to keep the stick upright. So for me, I use my eyes, the quadrocopter will use the cameras. I use my brain, the quadrocopter will use the laptops. I use my hand, the quadrocopter will use its motors. Let's see what it looks like. So you see that the quadrocopter can indeed keep the stick upright. And I can even nudge it around a little bit. We'll make it harder. Using this pointer, I can tell the quadrocopter to fly to a specific point in space. All the while, it has to keep the stick balanced upright. Now, when we remove the stick, I have to catch it before it falls into the propellers. There we go. Thank you. There's an important difference, though, between how I balance the stick and how the quadrocopter does it. For me, the rule I use to move my hand, I came up with by trial and error, by practice, and by intuition. So I had some idea what might work. I then tried it and saw whether it worked or not, and then I just kept practicing and practicing to keep the stick upright. For the quadrocopter, this was different. For the quadrocopter, we sat down with a piece of paper and we wrote down the mathematical model of how the quadrocopter works and how the stick that balances on the quadrocopter works. We then computed a mathematical rule that tells us how to create the motor forces that will move the quadrocopter while keeping the stick upright. The difference is that with this mathematical model, we could know whether this would work or not work without actually going out and building the quadrocopter. We could do this on the piece of paper. This means you can go out and design complicated machines, complicated interactions, and you can decide with these analyses whether the system will work or not work. You don't need to go and build all the expensive machines and try it out. These mathematical models tell us when something is easy, when something is hard, and when it is impossible. We'd like to show you something that's easy. Imagine you wanted to balance a glass of water on a quadrocopter. How would you do this? It seems like it would be hard. You probably have to constantly observe what the water is doing and then react to it to keep the water in the glass. In reality, though, it's really easy. You don't need to do anything special. The reason is simple. When we look at the mathematical model of the quadrocopter, we said there were only two forces acting on it. It was gravity, which pulls it down to the ground, and then this total thrust force, which pushes it forward. These are the same two forces that will act on the glass and act on the water. Gravity works on all things in exactly the same way. If the glass is attached to the quadrocopter, they will fall at the same rate. The water, as well, will fall at the same rate. That means if it was only gravity, the water would never spill because they would be falling at the same speed. The total thrust force will actually act to push the water into the glass. If you put the water flat on the quadrocopter, it will push the glass upwards, and the glass will push upwards on the water. Another way of thinking about it is to think of the water being pulled down into the glass by this total thrust force. That means no matter how we fly, the water should balance on the quadrocopter. Let's try it out. Again, I will use this pointer to tell the quadrocopter to fly to a specific point. Notice that the vehicle is flying quite quickly, actually, but the water just stays in the glass. Okay. So what we've shown you so far have been examples of where we needed to stabilize the system, where we needed to take something and make it stay where it was, or not fall over, or not explode. Next, we want to show you something where you need to do something more, where you need to plan a motion, where you need a motion planner. We'll have a quadrocopter take off in a second that has a badminton racket attached to it. The quadrocopter will have the task of hitting a ball back towards me. We will use a table tennis ball, this one here. To do this, you can imagine how you hit a tennis ball, for example. You need to bring the racket to the same point as the ball will be at the same time as the ball is there. You need to have the racket move at the right speed, and you need to point the racket in the right direction. These are the same things that the quadrocopter will need to do. This is interesting for us from a research perspective because every time I throw the ball, I throw it differently. And the system needs to measure where the ball is going, try to predict and react to these changes in the ball's trajectory in real time. Okay. Thank you. So I'd like to explain to you a little bit behind the scenes what's happening when the quadrocopter does this. In the meantime, my colleagues will set up for the next demonstration. On the projectors on both sides, we'll show you a video of the quadrocopter hitting the ball and what's happening in the background. So the video is a bit confusing, so I'd like to explain it to you step by step. You see me on the right-hand side throwing a ball, the bright white spot, at the quadrocopter. The quadrocopter has the task of hitting it back towards me. The first thing we do is we measure where the ball has been in the past, and we try to predict where it will fly in the future. This prediction is shown as the green curve on the figure. Along this predicted ball path, we can choose a point where we want to hit the ball. We then need to calculate a trajectory that will bring the ball from the point where we hit it back towards me. This is now shown as the light blue curve. We now know what we need to do with the quadrocopter. We need to bring the quadrocopter from wherever it is at this point in time to that point where the blue and the green curves meet. This is where the ball will be. And we need to do this at the exact same time as the ball gets there. What we do now is we plan the quadrocopter's trajectory. This is shown as the red curve on the figure. We do this continuously. Every 20 milliseconds, we get new measurements of where the ball is flying. This allows us to more accurately predict its path. We then choose another point where we can hit the ball, and then we plan another quadrocopter motion from wherever the quadrocopter is at that point in time to this point where we wanted to hit the ball. Let's look at the video again. I'm going to play the video one last time. Have a look at how the red curve changes as we get more information of what's happening with the ball. This is a powerful strategy because it allows us to plan the quadrocopter's motion at the same time as we are reacting to errors. So either we're learning more about how the ball flies, or we're correcting mistakes in how the quadrocopter flies the motion that we planned for it. The next demonstration will be somewhat similar. This time, though, we will have 3 vehicles interacting with the ball. So the quadrocopters are trying to throw the ball vertically upwards. To do this, they need to fly outwards and pull the net taut, and then the ball flies upward. Then they have to catch the ball. Now it is clear that here, compared to the previous one, we need to coordinate their motions very precisely. If one quadrocopter starts flying too early, it will pull the net taut before the others do, and the ball will end up flying in some random direction. Let's have a look at it again. We can also throw the ball towards a target. If we tilt the net slightly when we throw the ball will throw horizontally. And we can use this to throw the ball towards a target. Let's see what that looks like. We will now push the system to its limits. The quadrocopters will throw the ball 3 meters horizontally, then they have to rush to catch the ball before it falls to the ground. Try to notice how quickly the quadrocopters have to move after they've thrown the ball to get the net to the right position to catch it again. So my colleagues will quickly remove the net so we can continue with the next demonstration. In the meantime, I'd like to give you some key statistics for the system. We have 12 of these cameras on the ceiling that look down and observe what's happening. These cameras measure the positions of the quadrocopters, they measure the position of the balls, of the pointer, and of the stick. The information from these cameras is sent down to the laptop computers standing behind me. You can think of the cameras as a very fast, very accurate GPS system. In fact, they take these measurements 200 times per second. The computers then have the mathematical rules, these control laws, running on them, and they then decide how the quadrocopters should react to these observations. The vehicle then executes this command, and we observe whether it worked or not, and we send a new command. So 50 times per second, we send new commands. The demonstrations we've shown you so far have been very abstract and playful. Indeed, a lot of the work we do at our group is to push the boundaries of the technology rather than on concrete commercial applications. However, many people are looking at commercial applications of these vehicles. For example, you can use them to film an event from the air. Nowadays, it's easy to go out and buy a quadrocopter with an attached camera that can film an event. This is much cheaper than it would be to hire a helicopter with a pilot or to get one of those booms that they use in Hollywood. You can buy one of these and teach yourself how to pilot it. People also want to use these vehicles to carry goods around, either to deliver something you've bought online to your house within 30 minutes of you ordering it, or to move medicines and other critical goods around in isolated parts of the world. The idea is that if you have many of these vehicles distributed through the country, they can move small packets from point to point. You can imagine you might have a road system which is every rainy season gets washed away, but you still need to get the goods out. And if you had a fleet of these vehicles distributed through the country, you could move goods between the different stations. One of the things that will be critical, though, if these vehicles are to become extremely common, is safety. The vehicles are so popular because they're so simple. We saw they only had the 4 moving parts. The problem is if you lose one of the propellers, let's say you lose a motor or you lose the propeller itself, it's not clear what will happen. It seems like you just crash. This motor is producing force, but this motor is not. So the vehicle should just fall over and you'll crash. One of the things we've discovered, though, in our lab is that there's a way you can still fly the vehicle, even if you lose one of the propellers. We'd like to show you what this looks like. So notice that the vehicle is spinning. We're no longer trying to control its full orientation, but we can still control its position. I will again use the pointer to tell it to fly to a specific point. Notice it's flying slower than it was before, but it still gets there. This means that if you did use a quadrocopter at your wedding and you lost one of the propellers, say a bird flew into it, you don't need to crash and destroy your expensive camera, or even worse, injure a guest. You can still bring it safely home. We can go even further. I'll now remove the second of the 4 propellers. The vehicle will have only 2 of the original 4 propellers left, so we'll have lost half of the original inputs that we had, but we'll still be able to fly. Let's see what that looks like. Notice that the vehicle is spinning much faster now, but we can still keep it stable, and we can bring it back for a soft landing. The demonstrations we've shown you so far have all been specific to quadrocopters, but the entire field of robotics is currently very exciting. We know that robots build our cars. They do the welding, they do the painting, they do a lot of the assembly. Soon, the cars themselves will be robots. The car will drive itself. These automatically controlled cars will be safer than the cars we have at the moment. A robot does not fall asleep when it gets tired. It doesn't get tired in the first place. A robot does not get drunk. A robot does not suffer from road rage. People want to use robotics for other things as well, either to pick fruit on a farm or to take care of the elderly, to allow them to live independently for longer. One of my goals in this public lecture is to perhaps introduce to some of the young people in the audience some of these concepts, in the hope that they might also be interested in pursuing a career in this direction. I myself grew up in a town called Hartbeespoort in the northwest province of this country. I did my bachelor's degree at the University of Pretoria before I got a scholarship to do a master's degree in Switzerland, where I studied robotics. I'm still in Switzerland at the moment. I'd like to encourage the young people to consider a career in this direction. There are many opportunities, both in terms of research, in discovering new possibilities and creating new technologies, and in terms of commercialization, to bring these technologies to the market. Before we end off, we'd like to show you one last demonstration where we will be using, again, 6 of the vehicles at the same time. Thank you. So I hope I've been able to give you an insight into some of the work we do, specifically at ETH, but also in general as controls engineers. I hope I've been able to convey the enthusiasm we have for what we do and how much we enjoy it, especially to the youngsters, to try and convince them to join us. The Flying Machine Arena is a project that was started in the year 2008 by Professor Raffaello D'Andrea. Throughout the years, many people have contributed to this project to make it possible to do the things we do today. You'll see their photos on the screen. With me today are 3 of my colleagues. I'd like to introduce them to you. It's Federico Augugliaro, Robin Ritz, and Dario Brescianini. The four of us would like to very much thank the organizers of the conference for inviting us here today, for allowing us to hold this public lecture, and for making the entire process as painless as it has been. They were extremely helpful with the organization, with the infrastructure, and we'd very much like to thank them. Finally, we'd like to thank the audience for being here today and for their attention. Thank you very much.